Okay, welcome to this ACUR at ANU student presentation session. We acknowledge and celebrate the first Australians on whose lands we meet and pay our respect to the elders past and present. My name is Cheryl and I'll be chairing today's session for quantitative and qualitative data for tomorrow. Our first presenter for today is Darby Liersch. So please start when you're ready.
Hello everyone, can you see my screen? Just a quick check. Okay, perfect. Okay, good afternoon everyone. My name is Darby Liersch. I am an undergraduate engineering student at ANU. I'd like to start by acknowledging and celebrating the first Australians on whose traditional lands we meet and pay my respects to the elders past and present. I first want to give some context to my research project before I introduce the project itself, its aims and its main conclusions. I'm sure everyone here remembers the Australian Black Summer bushfire season of 2019 to 2020. This bushfire season killed 33 people and over 1 billion animals, raising around 80% of the Namadgi National Park in the ACT and causing significant economic and environmental losses. This was one of the biggest ecological disasters in the ACT, and we will continue to see longer and more devastating bushfire seasons because of global warming. It is for this reason that fire management is becoming increasingly more important. Fire management aims to protect human life, ecosystem, and biodiversity. It is achieved by managing fuel loads and vegetation, maintaining access to tracks and trails that support fire prevention, increasing community preparedness, and planning fire response. Fire simulators can be used by fire agencies to support all of these areas of fire management, and therefore has the potential to save lives and reduce the impact of bushfires. However, while all of the agencies of all the other states and territories in Australia utilise bushfire simulators, the ACT does not. And so what this project aims to do is to help fill this gap. In order to do this, we first investigated how different bushfire simulators model the spread of fire, and then use this knowledge to identify which commercial bushfire simulators that are currently available is the best one to use in the ACT. Finally, we demonstrated the use of the simulator's software in order to support further work that will be able to apply the selected simulator to the ACT. The first step in this project was to figure out how bushfire simulators actually model the spread of fire. So this is a general schematic illustrating the process that fire simulators use to model fires. First, you have user inputs, which include ignition location and time, topography, weather conditions such as rainfall, humidity, and temperature, and can also include suppression resources. So for example, fire suppression methods, location, and time. Simulators also have bushfire behavior models, which take these inputs and then use mathematical equations in order to predict the numerical value of different fire behavior characteristics. So for example, flame height, rate of spread, and smoke spread, which are some of the overall outputs of the model. Then bushfire simulators also use a simulation technique, which takes in some of the inputs and then also some of the outputs of the bushfire behavior models, and then uses these to predict the new fire front location at a given time. This results in other outputs, for example, the state of the landscape, which is whether regions are burnt, unburnt, or still burning. So there are many different fire behavior models that have been developed over the years, and different simulators can use multiple different fire behavior models. And for that reason, I'm going to focus a little bit more on them here. So in order to get an idea of the different fire behavior models that can be used, we can look at how they can be classified. So models can be classified in two different ways. Firstly, they can be classified based on the type of equations that they use. So for example, theoretical models are based on physical laws, whereas empirical models are based only on observed fire behaviors from experimentation or historical studies of forest fires. And then semi-empirical models are based on both theoretical expressions and empirically derived components. The second way in which we can classify these models is based on the type of fire that they model. So surface fires are fires that spread through fuel that is located within 2 meters of the ground. So all simulators use these surface fire models because this is the most common method of fire propagation. And then some bushfire simulators also include crown fire and spotting models, where crown fires are fires that burn through the canopy, and spotting is where an ember is carried by the wind and ignites a spot fire ahead of the fire front. Most bushfire behavior models are only applicable to the conditions under which they are derived in. And this means that most simulators can only be used without modification in the countries that they were developed in. Therefore, while there are many, many different simulators available from around the world, in order to select a fire simulator, I identified the bushfire simulators that were developed in Australia and that are currently used operationally by fire agencies. So this narrowed down the selection to 3 bushfire simulators: Phoenix, Australis, and Spark. So this was the full table that I looked at when comparing all of the different criteria for the 3 simulators, but for the sake of time, I'll just present a few of the results. So if we first look at documentation, we can see that Australis was the only one that had really poor documentation, and this makes it harder to understand and use the software. In addition, we can see that Australis is the only one of the 3 that doesn't have a spotting model. And this is a big disadvantage because this could be potentially used and it could potentially be a required functionality for the one that we want to use in the ACT. In addition, another consideration was how widely used the simulators were. So Phoenix and Spark are used in most states and territories in Australia, whereas Australis is only used in Western Australia. And so an advantage of choosing Phoenix or Spark is that it allows interstate cooperation. There will be more support and training available for end users, and also means that there will be a lot more operational testing and validation on these simulators since they're widely used, and this could likely lead to further improvements. These were 3 of the main reasons that I eliminated Australis from consideration when comparing these simulators. And then I carried on Phoenix and Spark to compare them to see which would be the better one. So if we look at the different models that the simulators use, we can see that they all use different surface fire behavior models. So Phoenix uses 2, one for grasslands and one for forests, whereas Australis uses 4 for different fuel types. And then Spark is interesting because it allows users to define the bushfire behavior models that they want to use for the different user-defined fuel types. And this is actually a really big advantage, as while the other 2 simulators have models hard-coded in, Spark is a configurable simulator, which means that it can use models that are applicable to the given location and can also be updated with models as new research is done. The next thing that I'd like to point out is the scalability of the different simulators. So Spark was created using the OpenCL framework, which can utilize multi-core CPUs and GPU hardware. Therefore, Spark can be scaled to run on hardware ranging from desktops to high-end computers, which allows it to easily be used to analyze thousands of scenarios with slightly different input conditions at once. This is really useful because it means that it takes into account the uncertainty from all the different inputs. In contrast, while Phoenix can still be used for ensemble analysis, it's not as scalable because it's limited to CPU and multi-core processing. Therefore, it was because of the scalability and the configurability that Spark was ultimately chosen as the better simulator to use. Therefore, the next step was to actually run the Spark software. So we used the Spark demo version 1.1.2 to do this because it was freely available and didn't require a license, which is quite difficult to get. The demo version is highly configurable in that it allows users to define the inputs that were used, the different fuel types, the bushfire behavior models that were used for each of the fuel types, and also the outputs of the simulation. And this demo version came with 3 sample projects, which had input data for 3 defined regions. One was in Blue Mountains National Park in New South Wales, one was in Fawcett in Tasmania, and one was in Steeles Creek in Victoria. Therefore, as we were just trying to get an idea of how the simulator worked, we decided to choose ignition locations within these 3 regions to get an output. For the sake of time in this presentation, I'll only discuss the outputs from the first sample project, which focused on the Blue Mountains National Park. So here is one of the outputs from the sample project, which shows the predicted spread if a spotting model isn't used. So we can see the ignition location here in red, and the black area is a user-defined unburnable area, such as a fire break region or a previously burnt area. And the fire was projected for 9 hours, and you can see the isochrons for the fire progression. Then if we look at the second output that we had, this shows the fire at the same ignition location and the same time, and also projected for the 9 hours, but with spot fires included. So you can see how much further a fire spreads based on the black unburnable region, which you can use as a reference. So this means that it sort of demonstrates how much of an impact spot fires have and how much further it can progress if you include the spotting models. And so these 2 examples and the rest of the outputs demonstrated how the simulator could be run and the different components that could be defined by the user. So fire simulators. This then informed the selection of the bushfire simulators, in which Spark was selected as the best simulator to use in the ACT. And finally, we demonstrated how the software was run in order to predict the spread of fire. And then future work is suggested to obtain a license to access the full software, because this can then be used to investigate the Spark source code to determine exactly how it applies the bushfire behavior models in order to gain a better understanding of the effective use and also the limitations of the Spark software. And finally, Spark can also be used to compare the predictions of different bushfire behaviour models by applying them to historical fire data from the ACT in order to determine how a actual fire spread observed. And this will allow us to determine which of the bushfire behaviour models are the most accurate for the ACT, and therefore which models should be used to operate Spark. To contact me using my email if you have any further questions after this conference. Does anyone have any questions they'd like to ask now?
Thank you so much, Darby, for your presentation. If judges, you have any questions, you have 5 minutes to ask and just shoot them through. But yeah.
Hi, Darby. Thanks for that presentation. It was very interesting and quite, I really like systematic methodologies, and you made that really quite clear. So well done. I was wondering, because Spark is so user-friendly and you can put so many inputs into it, you said that you only focused on Australian systems because there's so many differences around the world, but because Spark appears to be so, I suppose, mobile with its inputs, do you think it would be able to be applied in other countries, such as where we have a look at the California wildfires?
Absolutely, I actually do. So the difference between Spark and every other simulator that I've seen, because I did look at the ones in the other countries too in order to eliminate them, is that with all of the other ones, the models are hard-coded in it, and the models are the ones that make it inapplicable to other countries because they use the fire rating systems and the types of fuel that you have from other countries. Whereas Spark actually allows you to choose the fuel type and choose the bushfire behaviour model, and you can select models and fuel types from the other countries. So you could definitely apply Spark to different countries by completely configuring it for those other conditions.
Thanks.
Hi, Darby. Thank you very much for an excellent presentation. That was really, really interesting and very informative. Also, the using Spark modeling with the 2 different settings with and without spotting was really interesting. You said that you also assessed the other model. How different was it using the other model I'm assuming you modeled the same Blue Mountain fire using the other model. How different was the output, just out of curiosity?
So which other model are you referring to? So what we did was we used Spark for multiple different locations.
Right. So you didn't actually, so you had 3 softwares, I suppose, for Australia, Spark. I can't quite remember the names of the other 2, but you said that was the second one that was also relatively widely used.
Mm-hmm. Phoenix was.
Phoenix, that's one. Did you try Phoenix on the Blue Mountain location?
So the issue was that we can't actually access Phoenix software because it's currently under development. So Phoenix recommended using the Spark demo version to test it, which is obviously very frustrating. So we did just use Spark, but what we did was we used it on the 3 different locations. And you can't tell on this one, but the way that they did it is they have 2 very rigorously tested and very widely used models for grasslands and forests. Yeah. But then for their 3rd model, they use an urban model, which is just a dummy model. So it's something like the rate of spread in urban areas is proportional to the wind speed, and that was it.
Right.
And so that's why if you look at the second one, while it does show how much further the model spreads with spot fires, it's actually not entirely accurate, because if you see here it's hit, I don't know how to point, but if you look at the right where it's actually hit the urban area and there's urban area underneath where it's spread, it's actually spread a lot further than what it would actually using the dummy model for those locations.
That's really interesting.
Does that make sense? So while spot fires do make it spread a lot more, the different models that you use really impact how the model, how Spark actually models it. So if you have an inaccurate model, like this dummy model is, because obviously it's not just proportional to the wind speed, Spark as well. What you're doing, if you're not using the correct models, you're not going to get a very accurate result. Does that sort of answer the question? I made it. So the sample projects for all using Spark.
That's very interesting. Thank you very much.
Okay, and with that, we just ended on time with our Q&A time. So our second presenter for today is Xuyang Shen. Could you please start when you're ready?
Good day. I'm very glad to be here and present the research feature selection on thermal stress data set. I'm Xuyang from the Australian National University. In this 10-minute presentation, I will first introduce myself and then I will talk about background, dataset, model, experiment, and results. Hope you enjoy it. Yep, this is me. I'm in Master of Computing Advanced Program in ANU. I previously did several research related to generative adversarial network, biostudy, and speech recognition. Some are done in my bachelor degree and others were during my master degree. I'm currently pretty interested in transfer learning, transformer, and general AI. Let's move on to the background. Stress as an emotional language of human represents the body reaction to the environment. Less stress might be beneficial to our body, while high stress might let us feel less energetic and even cause other body issues. Therefore, stress detection is important in our daily life. A common solution for stress detection system is based on physical appearance of objects. It requires an RGB camera and a thermal camera. In this project, our dataset is collected from those two kinds of devices. To make the system efficient and high accurate, feature selection is a necessary processing operation. Overview for a machine learning task. Feature selection is in the beginning stage. It can filter out meaningless information and improve the model performance. In this paper, I will talk the three methods of feature selection algorithm: correlation analysis, magnitude measure, and genetic algorithm. Correlation analysis is from information theory. It aims to measure the strength of linear information between features. Magnitude measure helps us to consider the feature relationship in neural network through local search. Genetic algorithm is a statistic search to approach global optimization. So don't worry if you are not familiar with this concept. I will introduce them in detail later. After introducing background, let's move on to a dataset. The dataset we use is thermal stress dataset, also known as ANU stress DB. The dataset is from a human-computer interaction experiment about stress simulator. There are 31 people involved in this experiment. Their facial information was recorded by two cameras, one RGB webcam and one thermal camera. To protect the privacy, the public version is processed by principal component analysis. It's a common operation in HCI experiment. Therefore, the released version contains 620 records with 5 features extracted from RGB image and 5 features extracted from the thermal images. The label of each record is binary, either stressful or not stressful. Although the dataset is well balanced between these two classes, it's still very hard for model to make the correct prediction. Unfortunately, the dataset contains lots of data noise, like other HCI datasets. The TSNE analysis, we found that a high similarity between these two classes. It means like most of the data features from these two different classes are overlapped. Before talking about the experiment and the result, I would like to introduce two machine learning models that help us to measure the performance of each feature selection algorithm. Support vector machine is a supervised machine learning model that performs both linear and nonlinear classification. In this paper, we use RBF kernel and leave all hyperparameters as default. Artificial neural network, also known as fully connected neural network, is the second model we use. Compared to the deep neural network, it has simple architecture and less hidden layer. We use 4-layer neural network in our experiment with ReLU as activation function. For the optimizer, we apply ADAM with 0.0003 weight decay. Correlation analysis indicates the dependence of or relationship between two data variables from a statistical perspective. From the formula, correlation is a normalized covariance value, and the range is between -1 to 1. -1 means highly negative correlation, and 1 means highly positive correlation. We run the experiment and also run the algorithm between each feature and the label and list the result in the table. There are 4 attributes are lower than 0.005, which are thermal feature 4, thermal feature 5, RGB feature 4, and and thermal feature 1. After we remove this low correlative feature, we find that it contributes little to the performance of improvement. Bacterial Measure is an analysis applied for input neuron in trained neural network. It measures the impact of input neuron to output neuron based on the weight value of the layers. Input neurons with high weight means that input features are important. Compared to the correlation analysis, the magnitude measure focuses on the impact of dataset property on neural network behavior. The results shown in the table indicate RGB3, thermal1, and RGB1 negatively contribute to the neural network performance. After we remove those features, we found that magnitude measure can provide variable guidance on feature selection for neural network. The magnitude measure is only suitable for neural network and is also a local search. Therefore, we introduce another feature selection algorithm that uses global search, genetic algorithm. It is derived from natural selection. It performs a statistic search for an optimal solution based on 5 components. Firstly, we should encode the variable as a chromosome. You can treat it as a DNA. For example, we have 10 features here. We can set down the chromosome with 10 genes, like 5' and 5'1". It means that all RGB features are selected and all thermal features are not selected. Secondly, with the encoding of the chromosome, we can initialize the population. It's better to be well-distributed and also has a large diversity. Then we have lots of feature options. We can train the model and record the test accuracy. Thirdly, we need a fitness function. It can be accuracy or loss. In our paper, we use test accuracy. Besides, we also need to set down the number of generation, which refers to the termination state. Thirdly, we need, in the first step, we need a selection algorithm. Because in natural selection, only a few individuals can survive. There are lots of selection algorithms we can use, and also you can design a new selection algorithm. But we should keep in mind that this algorithm should not always pick the best individuals. The last step is reproduction. We select some chromosome from this generation to reproduce the next generation. Usually we use uniform crossover, which means one parent with another parent. After generating the baby chromosome, we also need to randomly change some genes. This operation is called mutation. After hundreds of generations, we select the final chromosome with highest test accuracy. The result of applying genetic algorithm in feature selection are shown in these 2 tables. Genetic algorithm applied with artificial neural network has a large improvement in the test accuracy, which achieve 90% of accuracy at maximum. Besides, genetic algorithm can also improve 80% of test accuracy of sparse vector machine as well. In this paper, we studied 3 different feature selection algorithms: correlation analysis, magnitude measure, and the genetic algorithm. With machine learning model, we also indicate lots of findings. Hope this finding can improve the accuracy of current stress recognition system. If you are interested in our work, you can scan this QR code and read the full paper. And that's all my presentation. Hope you enjoyed. Thanks everyone, and keep safe.
Thank you, Xuyang, for your presentation. Now we have 5 minutes for a Q&A. So judges, if you have any questions, feel free to ask.
Hi, I probably missed it in your presentation, but I'm not quite clear on exactly what the connection with your genetic modeling was. Can you maybe explain that again in more lay terms?
Yeah, of course. So genetic algorithm is like is very similar to the natural selection in biology. I mean, and the genetic algorithm has 5 components. Exactly the same as in natural selection. It first has a chromosome. It's like a DNA or like a list of genes, and we can encode the variable in our experiments into the chromosome. For example, we have 10 variables here, so we should set the chromosome with 10 genes. And secondly, we should have the with the chromosome, we should have the set the population numbers. For example, we can set 100 population at maximum with 10 features. And also we need to set down the generation. One generation means like one chromosome to produce a baby chromosome. And thirdly, we should have a fitness function, which is very similar to a loss function in machine learning model or a test accuracy. So with in some scenarios, the fitness function can determine the end state or termination state of the whole genetic algorithm. And the next step is reproduction. So we have some chromosome. We need to select the best chromosome in this generation and to produce baby chromosome. And also with the producing baby chromosome, we also need the mutation. So in mutation means like we need to randomly change some gene, for example, flip 0 to 1 or flip 1 to 0. And after several kind of loop, we have the final stage, which have a final chromosome with highest test accuracy, means like the best chromosome with like best DNA we have in this scenario. So that's the whole story.
Right. Thank you.
Yeah, no worry.
Any other questions? Last minute? Oh, okay. In that case, we might move to our final presenter for today, Amber Anderson. So please start when you're ready, Amber.
Thank you. So hello everyone, my name is Amber and today I'm going to be talking to you about my research project, which is Those Who Can't Do Teach, High Achieving Students' Perceptions of Becoming Teachers. So a brief outline of my presentation today. I'll briefly outline the problem, the research problem that I have, the research question, research design, the key findings, and finally a quick conclusion. So firstly, let's frame the research problem. Teachers in Australia play an incredibly important role in our society because they act as mentors, provide expertise to students, and also act as role models to Australian youth. So for our future generations, their academic success, their self-confidence, and even their life opportunities are actually dependent on the quality of teachers that they have. So surely this would mean that as Australians, we want the best and brightest and most passionate people going into teaching. However, this is not always the case. What if I told you that in 2015 in New South Wales, school leavers who scored in the bottom half of their cohort made up 50% of teaching degree offers made that year? Furthermore, just 7.16% of teaching degree offers were made to students with an ATAR of over 90. And over the past 40 years, there's been a steady decline in the academic capability of our teachers. Now, this is really worrying and shows that a significant decline in Australia in the teacher quality of our teachers is a really significant challenge that Australia is going to face over the coming years. So how can we address this? One potential way to improve the teacher quality is to attract high achievers to the profession. Now, this is really a really well-established method in the literature, and a lot of policy documents as well state that we want to attract the best and brightest into teaching. And the best and brightest has been described as students with excellent academic ability and communication and interpersonal skills. However, the teaching profession in the past has really struggled to attract these high achievers, and teaching has been perceived as a career that has low social status and requires a minimum skill. Hence that horrible quote, "Those who can't do, teach." So how can we attract these high achievers to the profession? We need to figure out how high achievers actually perceive the teaching profession, because this will allow us to create really effective recruitment strategies to attract high achievers to the profession. However, there's minimal research actually existing on the overlap between the teaching profession and perceptions of it and high achieving people themselves. So that's where my research comes in, and looking at how high achieving tertiary students are perceiving teaching as a potential future profession for them. So for example, looking at their perceptions of teacher salary, of teacher status, and how that might reflect on what they want from their future career. So going into research design now, it's a political science background, so it's based on studies of interpretivism. So I'll go through that now. I chose a case study methodology, and this was a focus on one Western Australian university. And from within this university, participants were selected from 2 separate groups. So the first group was called the Bachelor of Philosophy students, and this Bachelor of Philosophy in this university is a high achieving degree for high achieving students. So the entrance requirement to the degree is an ACUR of 98. And students within the degree can study whatever discipline they would like, from science to arts to commerce. The second group of students was a Master of Teaching group, and within those Masters of Teaching, only high achievers were selected. So this was defined as students with a weighted average mark in their university course of over 75%. So the high achieving Bachelor of Philosophy students were originally chosen because they are outsiders to the teaching profession. They have not yet chosen, or perhaps might not choose, the teaching profession as their career. And studies in the past have focused on basically teachers themselves or student teachers, and haven't got this perception of people that are external to the teaching profession. And it's really important that we actually consider these people's perception, because that's who we're trying to attract into the teaching profession. The Master of Teaching students were then chosen because they offer a really in-depth perspective on the teaching profession, because they gained more exposure to it after choosing the profession. And in addition, I conducted an exploratory survey with 152 respondents, and this survey and the analysis of the survey informed the development of interview questions. And then a consequent focus group interviews were conducted with 30 participants across both of the student groups. The analysis of the data from both survey and interviews was based on interpretivism. So this is pretty much central to interpretive analysis, is a focus on examining meaning-making processes. And this basically means that it looks at participants' perceptions and meanings of the world around them to make a really context-rich research report. And so it really foregrounds the voices and the perspectives of the participants when analysing the data in this way. And in reality, this means that the data is coded to find this basically means finding key categories within the data. And from there, an inductive process is basically built. And an inductive process pretty much means that from the raw data, you're building key categories and themes into more general broad themes until a theory or final findings are developed. So this leads me to my key findings. So overall, high-performing tertiary students have perceptions of the teaching profession that actually discourage them from perceiving teaching as a future career path. And these are broken down into 3 key subpoints. So high-achieving students experience a lot of social dissuasion from becoming teachers. And this social dissuasion was experienced from social norms, from their parents who encouraged them not to be teachers, from peers who looked down on teachers and therefore they felt they couldn't become teachers, and even from mentors and teachers themselves who told them that they should not waste their skills, as you can see in that quote there, and to do something that's more worthwhile of their strong abilities. High achievers are also strongly encouraged to follow more prestigious pathways. The more traditional pathways that high achieving students follow include medicine or law or engineering. So they tended to feel that they were being pushed or channeled down those pathways and dissuaded from the teaching pathway themselves. In addition to this, the second point is that the high achievers that were attracted to teaching or thought it might be interesting were actually put off teaching because of negative perceptions that they held about the teaching profession. So one of these really common perceptions they held was that teaching had a lack of intellectual challenge. High achievers really wanted intellectual challenge within their profession. And they perceived teaching as being too repetitive. They didn't want to teach the same content year in and year out. So they thought that it would be too boring and not challenging enough for them. The second thing that put them off was that there was going to be a lack of appreciation for them in their work. And this coming from students not giving them enough respect, and also from perceived low teacher salary. So these students basically said that salary is the society's way of labeling the value of a profession, and because they perceive teaching as having a low salary, that meant that they perceived that society then didn't perceive teaching as a worthwhile profession for them to go into. And the third common reason that many of the students said put them off teaching was challenges of classroom management and actually disciplining children. The third and final reason for high achievers not wanting to go into teaching is that they perceived it as a fallback career. In fact, every single student across the survey and across the interviews said that they believed Australia's society viewed teaching as a fallback profession. Now that's extremely shocking that every single person that participated in this study thought that teaching was a fallback profession, and quite worrying. You can see the quote below that the student said, "I don't want to teach if people will look down on me for doing a job that others do as a second choice." So they believed that they shouldn't do teaching because it was not a prestigious enough profession for them, because so many people saw it as a fallback career. So finally, in conclusion, high-performing students are put off teaching and discouraged from following the teaching pathway in their future because of strong social dissuasion they experience, a lot of negative perceptions they hold either picked up from social norms or from their peers and internalised themselves, and also the widespread perception of teaching as a fallback career. This research has really strong implications as it shows a lot of barriers and obstacles high achievers need to overcome in order to actually choose teaching as their future profession. And this could inform recruitment strategies for universities and for state governments to better attract high achievers into teaching. Teachers play a really, really vital role in our society, and it's really important that we ensure the quality of our teachers by attracting high achievers and the best people into teaching, because this will ensure the future prosperity of Australia. So thank you for listening. That's all I've got for you. If there's any questions, I'd love to hear them now.
Thank you, Amber, for your presentation. Yeah, so as Amber said, if anyone has any questions, judges, we have 5 minutes. So ask away.
Hi, Amber. I really enjoyed that that presentation. It's a really interesting topic, and I think I can personally relate to a lot of that, coming up both as being a coach and then going into academia. And I suppose, do you have, or through your research, did you find any ideas or were there any key findings about how to challenge and overcome those boundaries that do prevent high achievers from going into teaching?
Yes, absolutely. I didn't go into it in the presentation just due to the time frame, but the second half of the research was addressing potential policy implications and ways that they could overcome these barriers. So it's very contested within the literature, but ones that have come up in the past have been raising the ATAR entry standard to the teaching profession, because a lot of the university courses entry ATAR standards are quite low compared to the more traditional high achieving pathways such as medicine and law and engineering. And a lot of the students within this research project said that they initially considered teaching, but when they saw the ATAR entry was 60, 70, they thought, oh, I don't want to waste my high ATAR. I may as well choose something that is challenging me, such as a law or engineering undergraduate degree, and then maybe later on I'll go into teaching, but that rarely happens once they've started down that course. So similar to this, how the low salary seems to label the value of the profession, they saw the low ATAR as more of a signifier of the value of teaching and the difficulty. And going back to that intellectual challenge that high achievers really care about, if the ATAR entry to the teaching course was low, then they thought it would be easy and they want to do something that's more challenging. So one of the arguments is to raise the ATAR entry to teaching. And then an accompanying one to that is also the salary. So teacher salary isn't actually low for graduates. It's one of the highest salaries for university graduates, but a lot of the perception just isn't there. A lot of people think that it's really low. However, over sort of 20 years, that salary does begin to plateau. And once you've reached that sort of top level of teaching, it doesn't really increase much more. So for example, in other professions high achievers might want to go into, such as even consulting or engineering or finance, you can continue to grow your salary as you progress in your career, whereas with teaching, that doesn't happen so much. So another sort of suggestion to try and attract high achievers was to incorporate financial incentives later down the path where they could actually progress in their careers similar to other career ladders. Yeah.
Brilliant. Thank you so much.
Thank you, Amber. Excellent presentation, but unfortunately, I don't have any questions at this point.
No worries at all. Thank you.
Okay, in that case, that brings us to the end of today's session. Thank you to our judges, Dr. Ulrich Schumann and Ms. Hannah Clark, and congratulations to our student presenters for presenting today. This recording will be made available online following the conference, and we hope to see you again, and definitely in our conference sessions today, as today's our last day. But yes, have a great day, and great job for presenting again.
Thanks, everyone. Good job.
Thank you.
Thank you.
Thank you. Bye.